Hey, good evening. My name is Brian Ridpath. This is my case study for Crimson Global Academy. I'm going to be talking about a little bit of trigonometry. Let's get started. And good day. Today, hi students, we're going to be working on some pre-calculus concepts. We're going to focus on the graphs of the sine and cosine functions. And we're going to have a couple of goals today. All right. Goal number one is we want to spend our time graphing using transformations. Goal number two is we want to learn to leverage our technology to help us check what we're doing and make sure that we have actually acquired the knowledge and the abilities that we want to have, and then be able to understand what we're looking at when we see technology. So there's a lot in the check process. So it's not just about using the technology to graph, okay? And then goal three, we want to look at some problem types using multiple representations and so forth. And we'll get to that towards the end of class. All right, so let's get started. So, are you all doing good? Can you see the graph well on your screens? Just give me some thumbs up and let me know if you can see everything clearly. Okay, that sounds good. All right, so what we're going to do then is we want to look at the graph of y equals sine x. Now, we've worked on this for the last couple of days as we've been studying graphing and looking at sine. And we want to ask the question, what do we know right now? What do we know? What have we figured out so far about the graph of y equals sine x? And so let's take a look at that and see what we can point out. Or actually, why don't you guys go ahead and write in the chat, or you can even use the mic and give me a shout out and tell me a couple of things here. All right, that's excellent. First of all, it does go through the origin. All right, that's a great thing to know. Oh, excellent. Somebody says it's symmetric with the origin. So we do have symmetry with the origin. What else? Oh, maximums and minimums. So we have a lot of maximums and minimums. And in fact, what do you notice? The max value is always what? No, it's not pi over 2. The max value is always the y values. When I talk about what is the maximum, I'm asking what are the largest y values, or the minimum, the smallest y values. And if you remember right, then where does that maximum occur? That would be the x values. Oh, so the maximum values of 1 look like they occur at odd multiples of pi over 2. All right, if we look on the graph, we can see that every odd multiple of pi over 2 has a maximum or a minimum. So the max values are y equals 1, and the min values are y equals -1. So good. That's true about this all the way through. Okay, let's see. Anything else that you notice? It's kind of a reflection. Okay, that sort of makes sense. What we see is that we have this sort of repeating pattern, and then if we shove this over and then reflect it, we sort of have that. So kind of a reflection. So yeah, there's this repeating pattern going on where we're going up and down forever in both directions on the number line. We actually call that periodic. This is a periodic function. And if functions are periodic, they have a period. Does anybody remember what the period of sine is? Good, 2 pi. So this repeats every 2 pi. So if we look at this, that's 2 pi, then 2 pi to 4 pi, it'll repeat that, and 4 pi to 6 pi, etc., etc., etc. Okay? Anything else? Well, that's pretty good memory. You guys are doing great. So let's move on to the next. Well, let me stop here for a sec. Okay, so I cleared the screen, and so what I want to talk about is using the periodic idea. We tend to repeat numbers in the graph. So no matter what I do to this graph, if I take this graph and I make it taller, or I make it shorter, or I squeeze it together like an accordion so the bumps go up and down faster, or I spread it out so they go slower, what's going to happen is numbers are going to repeat themselves. Notice how we repeat our x-intercepts, right? Notice how we repeat maximum values and minimum values. So what I want to do is I want to talk about these values right here. I like to call them key values. And when we go to graph sin x using transformations, it's really helpful to remember these key values. Now you'll notice that what it is it covers one period. Covers one period. All right. And when it covers that period, all right, we also have one max and one min. And what's really interesting is there's symmetry in this. You'll notice that the period goes from 0 to 2 pi, but halfway we go through the value of pi. All right. So you could actually divide this in half, and that would be the middle. So if you know the period is 2 pi, then if you divide 2 pi by 2, you know where the middle is. Now, the other thing we notice is that the maximum and the minimums are halfway between the first point and the middle point, and the middle point and the last point in the period. And so we could divide that distance, which is now half a period, by 2, and that would help us find those values. Okay? Now, the nice thing about this is once we know the period of a trig function, we can essentially say, oh, my period starts at 0 and it goes to 2 pi over 3. Well, if I divide that in half at pi over 3, that's going to be the middle point right there. And if between this 0 and pi over 3, if I divide that in half, which is pi over 6, that'll be where the maximum is. And if I go pi over 3 to 2 pi over 3, this will be 3 pi over 6 or pi over 2. And that'll be where the minimum is. And I can use these key points to help me graph. And the secret is really knowing the period and knowing where it starts. All right, starts, the starting point. And the starting point is always associated with a term called the phase shift. And so let's go on now and look at some more transformations here. So before we moved ahead, I wanted to talk and remind ourselves about the transformations of algebraic graphs. Now you'll remember, you've probably talked about this in Algebra 1, right? You've probably talked about it in Algebra 1, Algebra 2 for sure. You'll remember we talked about it in the college algebra portion of this course as well. And you may have even talked about it in geometry. And possibly even your middle school math classes, 7th, 8th grade math, you would have talked about transformations, mostly in a geometric sense, but you would have talked about these same things: reflections, translations, and dilations. And that's all we are looking at here. So we have some very simple algebraic functions. We have an x squared type graph here. And then this one over here is an x cubed type graph. And you should remember those from last semester. And if you remember, if we were doing reflections, all right, reflections, if our main graph is the blue one, and that is f of x, then if we have a negative times the whole function, or times the main part of the function, then that negative will flip the graph over the x-axis, okay? If we have a negative times the variable, that will flip the graph over the y-axis, okay? Now, I want you to think through this again. We've talked about this before, but we want to think, why does that make sense? Well, if you take a negative times the function values here in this first case, a negative times the function values, okay? That means you're taking a negative of the y value. So if I have a y value here and I take the negative of it, that puts it down here. That's why it's a reflection. Now, in the same way, if I pick an x value that I want to plug in, and then I take the negative of that x value, that's why I end up reflecting over the y-axis, flipping over to the other side, okay? So that's reflections. Translations kind of follow the same process. We translate left or right, and then we could have something like f of x minus 2 or f of x plus 2 and our original function f of x. And then we could have f of x plus 3 on the outside or f of x minus 3 on the outside. So this situation here, this moves us up and down if we're on the outside. So notice we find the y value first, then we add a number to it. So it just takes our current y value and moves it up 3 units. Wherever the current y values are, they're moved up 3. Okay? In this case, we take our x value, and when we say x minus 2, this is really written as x minus h. So if you see x minus 2, that means h equals 2, which means you're adding 2. The original x value is 0, so I'm adding 2. And I know that seems a little odd on the signs, but if you remember, that's how we have to interpret that. We have to understand it based on the formula. And since the formula has a negative or a subtraction, that means if we subtract a number and it looks like x minus 2, then that number we're subtracting is a positive, okay? And so we move to the right. And then the x plus 2 would be x minus a negative 2. So that means we move to the left. And then that's why we move right or left, okay? Now, then we come to dilations, and dilations are basically like reflections in that we're multiplying the function either on the outside or the inside of the function. And if you multiply on the outside, you affect the y values, so you're stretching it. You're actually pulling the function each way, or you're compressing it, pushing it towards the x-axis. But if you multiply on the inside, again, If your original x value was 1, then half of 1 is 1/2. So you would end up giving the same y values, but your compressions are towards the y-axis or away from the y-axis. Now, this function looks a little like a trig function in that it goes up and down a little, and we'll see this accordion process quite easily on trig functions. So it's actually easiest to see on trig functions. Okay, let's move on. And so now we've figured out everything on this function here. We know where it reflects, we figured the stretch, we know the period changes, and we figured out there's no phase shift and no up-down shift. Calculating the amplitude and the period, we do that, and now we can use our keys. Since there's no phase shift, we start at 0 with this sine function, and the period's 8 pi, so we go to 8 pi. Therefore, we know our front and our back are on the x-axis. The middle is 4 pi, and if we cut that in half, that's where our min maxes are. But we're reflecting, so it's not the max first, it'll be the min. It reflects, and where the min would be at 6 pi, we would reflect up there. And so this would basically be one period of our sine graph. And so we could continue that and continue the labeling of our axes as we have done to get the 2 periods that I'd like for you to draw each time. And so there is the sine curve. Now, I'm feeling pretty comfortable with that, but what I'd like to do is I'd like to check. So let me snag our calculator here. So let's check with Desmos this time. And there we go. So we want to write our function in there. So let me shrink this just a little bit. And let me see if I can move it. It may not be letting me move that way. So let's do it this way. Let's shrink it. Oh, there it goes. All right, so it's -2 sine 1/4 x. So we're going to put that in here. So y equals -2. Go to our functions, grab sine, and 1/4, we can use the decimal, we can use the decimal here, 0.2, hit 2 decimals there. Always check for editing along the way, x. And so there's our function, so we've got it. And now we have it drawn here, but we need to check the scale correctly. So we need to go to the scale of our graph. And so my x values, I wanted to go, on my graph I did -8 pi to 2 pi. So I'm going to go there, and I'm going to go -8, and then do times 3.14159. That's close enough to 8 pi. And then we can go 8 times 3.14159. And that gives me my x's, and then I'd like the y-axis just to go up to from -3 to 3. And now I got to do one more thing. I got to scale the steps on the x-axis. That's really important, because otherwise I won't be able to tell what I need. And so in this case, I want them to be pi. I think I have a pi here. I think if I write pi, yeah, that works. I haven't done it for a while, so. All right. And so I think we have it labeled. And now I can shrink it just a little more. We can look at this and you can compare now this graph to our graph. Is the maximums at 2? Are they all in the correct place? So here's on this graph, if you wish, here is 8 pi is right there, and then 4 pi is there, 6 pi and 2 pi. And so do those match where our points are on our graph? So they do, so I'm feeling comfortable that I'm doing this part of the graphing right. And this is how we want to check, okay? And then we'll do the next one with our graphing calculator since we're taking the AP test and we want to be able to be able to use either Desmos or that, depending upon what we're most comfortable with. All right? Thank you guys. Hopefully that will help you, and we'll get on, and hopefully you guys like this if you're watching it. Thanks, Berna, and I believe Olivia. I appreciate the opportunity. Thank you.